Thank you for your patience in waiting, and hopefully you found some place here. So hopefully we can now all relax, or you can relax and enjoy the Impulse lecture of Sepp Hochreiter. So it's a big pleasure for me to introduce you, Sepp. I will not say much about him, so I'm really proud that we have one of the pioneers of deep learning here in Austria. And Sepp invented the long-term memory, which you all know is at the heart of current deep learning methods. And with this, I would say the floor is yours, Sepp, and hopefully it works now fine for the talk.
Thank you, Claudia. The mic is working well. Also, sorry for the delay. I will start with positive news. Sturm Graz won in the Champions League yesterday. That's some positive things. Yeah, but now I will go a little bit into this AI topic. Artificial intelligence is now in all news everywhere, and it promises to help to solve some of the big challenges of humanity, which would concern energy, climate change, food supply for the big cities, for Vienna, for example, healthcare, mobility. Think about self-driving cars and stuff. The success stories you hear right now is mostly deep learning. There were success stories also, as we heard, in symbolic AI, but right now there are many more things about sub-symbolic AI, in particular deep learning. I show you some success stories. One is Claudia mentions the LSTM, a very old thing, but it's the best method to predict floodings. Remember, even Austria had problems with floodings, and the system from Linz, you know Linz, so it's a small city between Vienna and Salzburg. These LSTM methods come from Linz, now are used by the US government, Canadian government, Israeli government to predict floodings. But more particular, Google, the Google flood warning system is using our LSTM systems because there were better sensor systems built by humans, which think about how much water is kept in the soil, in plants, in snow and stuff like this. That's a big success story. But be aware, governments not always follow what the things is predicting, even if it's correct. That's a different issue. You heard about another success story. There were these Nobel Prize things. There was a Nobel Prize in physics, but given to some who do not physics. They do neural networks, John Hopfield and Geoff Hinton. But there was another Nobel Prize, AlphaFold, which was really a breakthrough in structural biology to predict the 3D structures of proteins. You have only the sequences and predict the 3D structure. And they are also, therefore, the function. I will show a couple of examples in generative AI. Here is one. This was a problem to let this video running. That's a video completely made of thin air. It's a video made by an AI. You only give a prompt, like a woman walking in Tokyo, and this is the outcome. And I would say, if you can see it, quite impressive. But there are giveaways. If you know, if there's no camera, if it's zoomed in, you see on the sunglasses some signs, some letters, but the letters do not work out. They're not real letters. If you look like this, it doesn't make sense. Here, it generated something which is not, doesn't make sense. Another example, which also is funny, is this paper planes flowing through the wood, and only with a prompt, with a sentence, produce me a video like this. Also very nice, like a choreography, so flying through it. Quite impressive. Yeah. Another thing, I know on TU Vienna, the audience is very, very critical. Yeah? And nobody would believe this was made by an AI. But you believe mammoths do not exist anymore, right? Yes, most of them believe. Therefore, this video, there are mammoths on the video. Therefore, in this video, it has to be generated by an AI, because at the time of mammoths, there were no cameras. And if there were cameras, there were no mammoths. Now you believe me. I have to bring in this because I know this critical audience here. Another thing, you always have problems to look. You played as a child with this ant houses, but you can never look into it and don't know what's going in there. Now you can ask the AI to produce something like this. Look, you now see with a spotlight, you go into this ant nest. Yeah. Go into the cave. Yeah, also very impressive. I go in this direction. I will talk about this. But one moment, did anybody of you go to school? Nobody. I don't know whether you learned in school, or does anybody without school knowledge know how many legs ants have? 6. You learned it in school? You don't know, you know, you don't know. But you're right, if you look in school books or in Wikipedia, they have 6 legs. You count it here, oops, I have to, there's a video. If you count the legs, it's 4. It looks very impressive, but it was a diffusion model. At some point, it decided how many legs it will produce, but it has not the knowledge. It has no access to a knowledge base, does not know I have to produce 6 legs because nature decided for 6 legs. But it looks very convincing, but it's not fact-based. It's because some of this thing walk around. You see, all this generative AI stuff, it's not perfect. Let's go to another generative AI, ChatGPT. I hope everybody heard about it. I asked ChatGPT, who is Sepp Hochreiter. If it did not, because of sound, it's me actually. And this come out. And now I'm reading, I was born on June 4th in Scherding. And I get a shock because in my passport something else is. I called immediately my mother and said, what fake did you tell me? I said, no, ChatGPT is taking the wrong thing. It's true. What is in my passport, according to my mother, is true. I was there at my birth, but do not remember. Yes, but there are other things which are not correct. Here is a nice thing about the awards. So I'm sorry I didn't get this awards, but I'm now hoping to get the awards, because if all the reviewers are asking ChatGPT, ChatGPT will say I should get these awards. I'm waiting, but yeah, I'm waiting a couple of years already. Now to another topic, how AI is evolving. Here there are 3 phases of AI, as I see it. 3 phases of modern AI, of this deep learning kind of thing. Basic development, scaling up, and later industrialization or industrial AI. Here the 3 phases. This x-axis is variety of methods. The more to the right you are, the more methods are in use, are considered, investigated. The y-axis is the size, number of parameters of our models, the amount of data you're using to train these models. And this line here, which is in color, is the time. And you start with basic development. You're here. A lot of methods are investigated. Everything in academia is going on. Then you move on to a phase where the models became larger, the data become larger, and also, as you hear, this is a scaling up phase. The method variety decreases. And then you go further ahead. You turn over from scaling up to make everything bigger to try to use it, to make it usable for industry, for example. That's the industrialization, and later also going to individualization. Here, I think we are around here. The scaling up phase already saturated, and we are now in the phase of bringing this AI to industry, bringing the AI to companies, to applications. Where the method variety increases again. Now you have the big models, but to use the big models for different domains, you need again a higher variety. But we know this. The steam engine was one of the components which has driven the industrial revolution. And there was also first century basic developments, how with this steam you can push machines. Then in the 18th century, beginning of the 18th century, you scaled it up, you made it larger. There were different ideas how to do it. And then later, the industrialization phase came. The steam engine was on driving devices, cars, on devices in industry. It's not only you have the power, but to use the power, to use it efficiently and effectively. But there's another example. The Haber-Bosch process has a big impact on our society. This is the reason why we live in these big cities, why Vienna can exist. The Haber-Bosch process is the process how to make a fertilizer, to produce food in such a number, in such amount, that you can feed people, computer scientists in Vienna. And therefore, this had big impact, like the building of cities, the growth of population, the Haber-Bosch process. But also here, as you see, basic research, scaling up. For scaling up Haber, but I think Haber was not a BASF, it was Bosch. Haber got the Nobel Prize for scaling it up, for making it larger, having better catalyzers and so on. And later industrialization by Carl Bosch at BASF. A second Nobel Prize, two Nobel Prizes. Not for the basic research, but for making it large and for making it industrial scale. Here now to deep learning, that's deep learning. Basic research, I see the same three phases here in deep learning in this sub-symbolic AI. These are different persons like Leibniz, Legendre and so on, because they invented something like chain rule differentiation, stuff like this. And until the Sanucci Amari, Lina Mena and so on, this was basic research, how to train, optimize systems, neural network kind of systems. Then, after this basic research, a lot of ideas were out and so on, came the second phase. And this is the phase you are aware of. This is the phase of ChatGPT and stuff. It's the scaling up phase. To making the models larger and larger, throwing more and more data to the models. That's the phase we are now in, but it's changing right now. And where we in Europe, we in Austria, did not participate a lot. It was American companies doing that, scaling up, building the large models. ChatGPT is not from Austria. This was one of the scaling up stuff. This is one evolution of the large language models. It started with it was an LSTM model, and then soon 2018 came the GPT series, and you know GPT 3.5 is the ChatGPT thing. Here, looking at model size, for example, but you can look, model size would be the parameters at the bottom. 117 million parameters, 1.5 billion, 175 billion, and GPT-4, who knows, GPT-4. And this is with the size of this planets, the model size grew. And if you look at the data also grew. 1.3 billion tokens, 10 billion tokens, 300 billion tokens, and also the data increased. Model parameters and data increased. And this was what we're seeing right now, all these large language models. This was too much. Yeah, I go here. One word to the large language models. Large language models, you know, has nothing to do with artificial intelligence. Large language models is a database technology. You store also human text in a very smart way and try to extract it, which does not work very well at the moment. But this is not okay. Given it's artificial, I agree, but it's not intelligent. It's a database technology for me. But a knowledge representation is an important aspect of artificial intelligence. Insofar, yes, perhaps you convinced me. We founded a company in Linz where we don't want to miss the transition of scaling up, which the Americans do, the Chinese guys do. We look at it only. But if the transition goes into the industrializations, industrial applications of AI, we should be part, because we have a strong industry, especially in engineering, stuff like this. And AI revolution understood at scale, these large models, we were in the scaling up phase. Now we want to bring these large models into industry. We have to do this. And in this company, we have two pillars. One is AI for simulation, doing large-scale simulation, which numerics cannot do. We are 1,000 times, 10,000 times faster than the numerical simulations for very large simulations with 100 million mesh points or 100 million particles, where numerics doesn't work anymore. And XLSTM, which is an alternative technology based on the old LSTM as computer to transformers. Here, Johannes Brandstätter in Linz stands for AI for simulation, doing all this scaling up and then bring these simulation models into industry. And there's a huge request for this, because numerics does not work if it's too large. This is one of the things we can do. This, I think, was where you have a tool of particles and air, which took, I think, a couple of seconds for the AI system and a couple of weeks for the numerical simulation, only to get a few seconds of this thing. It's between weeks and seconds. That's the difference between AI. The AI method is based on the simulation data. It's not more precise than simulation, no. It's faster. And you see almost the same thing. And that could be a game changer. Here, another thing done with AI systems. In numerics, we can do it sometimes even real time, where the guys from the car company say, hey, we have to wait 3 weeks. Now you take a coffee. After the coffee, we have your simulation ready. That's completely different. And what we also want to do is, with AI simulation, that you change perhaps something on your car, and you see how the air is floating over your car in real time. And what they do right now, they change something, go home, days later, so I look up what came out. Yes, you know it, XLSM. The other thing we do in this company, industrialization, the question is, can we, with this old LSTM technique, recurrent neural network, can we compete with the new technique transformers? And the idea was, can we scale LSTMs to this big, huge, large thing? We do the scaling things also for our stuff. And yes, we can do it for up to 1.3 billion parameters. We outperformed other methods like transformers or state space models. Now we build a 7B model where we on the same level, like we are better than Llama. This is this meta stuff, but we or Olmo, but we are on par with other state-of-the-art models, but only in the 7B regime. And this with XLSM. We are as good as the others, but we are more energy efficient, and we are much faster. We are 100 in inference, not in training. In inference, we are 100 times faster because transformer has a quadratic. Who knows a little bit on math? Transformer is quadratic in the length of the produced thing on the context, and we are linear in the context. And quadratic is, for long context, worse than being linear. Believe me. Believe in math. You hate math, but believe in math. What can we get from AI in industry? Increase of productivity. And this right now is important for the industry in Europe, for the industry in Austria, for the industry in Vienna. That's important. To compete, we have to use this new technology. As we use computers, we have to use this new technology. Yes. Otherwise, we cannot compete on the market. Here, it's how good this AI technique is taken up. And you see Austria, oh God. Now you got a shock. Now you're frustrated. But no, we have something here. And there's a cluster, it's bilateral artificial intelligence, where we bring together symbolic AI and sub-symbolic AI to get into the next level. The next level is going to industrial scale applications to make it important for industry. One thing for industry is to make it robust, because if the thing does not work, the production line is standing. And there we can use symbolic techniques to ensure that nothing fails. Here in the new phase, we can go in with this new cluster of excellence. And you can be proud, you can be super proud. Vienna is part of this cluster. You see Agatha and Thomas, you already saw them here. Are you proud? Are you proud more on the Champions League or bilateral AI? You can be proud. It's really a success story. And we are looking for students, we are looking for new members. We're looking for more guys joining bilateral AI. Meaning you should now quit your professorship at TU Vienna and apply at bilateral AI. I hope to see you there. We need more resources. Please spread the word. We are looking for applicants on different levels, PhD, tenure track, and stuff like this. It's a big success story, and it's on the right time because we are entering the industrial phase. These are some of the heads in this cluster of excellence, and some of them should be familiar to you. I give you a minute, perhaps you recognize at least one. You should recognize one person somewhere. If everybody recognizes one person, I'll stop my presentation. Thank you.
Thank you, Sepp, for the great presentation. So what follows now is a short panel. And for this, I would please ask the panelists to come on stage. And there we have Axel. Axel Polleres is a professor at the WU Vienna. And his research is on smart web technologies, reasoning, knowledge representation, knowledge graphs. And now I would ask you first, Axel, to give a statement on the talk, but still I want also to introduce Francesco. Francesco from Freie Universität, Free University of Bolzano, Bozen, and his research areas of expertise are recommender systems, especially in a user-centered setting. So how can users interact with recommender systems in order that we really get what we want? So first of all, I would ask Axel to give you a statement, and after the panel we will have an open discussion.
You forgot one thing. Axel is one of our key members, board of directors in the bilateral AI. He's one of this famous guy on this slide.
So please.
Well, thanks a lot. Yeah. Thanks a lot, Sepp, for your inspiring talk and also for the many successes that you named on Sub-Symbolic AI. And it's really a pleasure to be able to collaborate on this in the BLI project. I wanted to start with, when we talk about what Sub-Symbolic AI can do and all the examples you showed. In some of the examples already it came across that there is a symbolic part in it. Yeah? So that basically the solutions that are built on top of sub-symbolic methods are hardly, that we see nowadays are hardly end-to-end neural network solutions, right? They usually have a symbolic component. Sub-symbolic AI does not work on its own and alone, maybe. Yeah? It works with symbolic techniques and it works with humans. And I think these are the points I want to stress a bit in the statement here. So first of all, when we talk about sub-symbolic AI and what has happened in the last few years, I guess like many of you, the question for me is not really what sub-symbolic AI can't do, but it's a bit like being a bit overwhelmed and asking myself what sub-symbolic AI can't do yet, right, to some extent. But you mentioned scaling factors. I think there's also impressive scaling in symbolic techniques. You mentioned knowledge graphs, right? So for instance, knowledge graphs, I was just at ISWC in the US last week, and there was essentially a talk by a big tech company. I shouldn't make advertisements here, but one of the people who wrote the original semantic web articles, and he mentioned that that they are dealing with graph databases with trillions of statements, with hundreds of millions of entities being served that they query and process in a day-to-day basis in operational systems. So I think that's also important. So also symbolic techniques are scaling, if you want to call knowledge graphs amongst them. I will get to that in a second. So what I also wanted to talk about is we should maybe take a step back and also ask ourselves what sub-symbolic AI shouldn't do. Not what it can't do, but what it shouldn't do. Maybe things that symbolic techniques and just computation can do more efficient. So for instance, databases. I was a bit surprised to hear you say that basically LLMs are just another database technology. I guess for certain things that we want to do with the database, there are more established, more robust symbolic techniques that we use to answer queries exactly and efficiently and use indexes to get exact answers. So we should decide when we need maybe inexact solutions or when we need to communicate and when we need to compute. Yeah, so I didn't find anything, but I wanted to take like this credit card pocket calculator with me and show it to you. Basically, when I do a simple arithmetics, and I can do it on a credit card pocket calculator, which is a machine that is very small and has much smaller than a GPU and has an integrated user interface even. And is probably much more energy efficient and can be solar powered. Then probably I don't want to do my simple arithmetics with an LLM. Yeah? Which, by the way, also when I ask an LLM for or arithmetics. Of course, this gets better and better, but there is provable limits of the bigger the numbers get, the divisions will get errors, right? Because LLMs are just not designed for doing this in an exact manner. Yeah? So what this brings us to is that what do we do? As humans, we use tools, and we have developed these tools. So I think it was also in Thomas' statement already in the morning that this is one of the points that we should always emphasize. The second tool that we are using as humans when we solve problems is search, right? We use search engines. We shouldn't use LLMs as search engines. Yeah? Language models as search engines is dangerous. Your example showed it, right? So basically when I want exact factual information, I won't get it because I get something that is probable, but it is not a referenced, basically, a statement. So what's interesting there is that there are of course techniques now that we are all looking at, like RAG, where we see that language models are trained to actually use tools or build. Typically RAG is now like fixed pipelines in the state of the art. It's not so much that they're automatically designing and maybe automatically finding services on the web that can do the job. So we need combinations of these tools, and we need tools. Right? So what else do we do as humans that language models maybe do not do so well yet? We collaborate, right? When we build knowledge, when we exchange knowledge, we collaborate. We build up something like, for instance, when you talk about knowledge graphs, some of you might know something like Wikidata, which is kind of a graph form of, or a database form of Wikipedia. And this is a collaboratively built knowledge base. Yeah? It's built by a lot of humans, by curation, and tools like also LLMs can help us to curate this knowledge, but this is largely a collaborative effort. There's a lot of research going in the direction of also having language models as part of agents. I think this is an extremely interesting directions. But these knowledge graphs, these collaborative built-up knowledge bases have another extremely interesting property. We can observe how they develop, we can observe how knowledge is curated and how knowledge is developing there. So we can learn, maybe combining symbolic and sub-symbolic methods again, how to better curate this knowledge. And I think this is an extremely interesting direction. Then last but not least, so we communicate. So we talk to each other. And let's be honest, language is also symbolic in a sense. So we use a limited number of symbols in this interface, which has almost infinite use. Yeah? It's not always precise, but it's fascinating what we can do with natural language, which is a narrow interface in a sense. Yeah? If we compare this again to strict symbolic representations like we have in knowledge graphs are also not 100% precise always. They are in fact, so they are typically not complete, they are typically containing inconsistencies, and they're somehow in the middle between databases and language. So I think that's why it's an interesting approach to think about what is actually the sweet spot for an interface of agents to communicate with each other. And what I mean with that is, for instance, so the holy grail of our research community, Frank van Hamelin was here, I think you might remember that, was at some point semantic web services. So the idea was there, really this idea was, which I was starting with, using tools and services that are available on the web on the fly to solve problems, right? So this is essentially a bit this semantic web vision. Now I think what's this question of the right interface is a key question to solve this problem, because we need to think about natural language is an extremely good interface that we can use to explain each other how to use a structured service or how to query something on the web. And but typically they have structured inputs, such services, right? And what happens when we compose services is we write a lot of wrappers and so on. I think language models can actually help there because they are very good in producing wrappers or language code, in translating. And there is a lot of possible connections there in order to build better systems. Yeah? So what I wanted to get down to in summary is LLMs cannot and shouldn't probably do everything alone in end-to-end solutions or sub-symbolic methods. Symbolic methods are very important there. Then using tools is one thing, collaboration is another thing, and the third thing we should think about is what is the right interface and whether it's actually natural language or whether we can use LLMs to converge to standardization. I conclude maybe with a joke. So basically when we talk about service interfaces and standards in standardization, there's always this joke. So if you have 12 different formats, then we need a standardization group that unifies them, and in the end we have 13 different languages or interfaces, right? And maybe LLMs can help us to actually really converge in some of these interface questions and find a better one that is really a standard interface for services. Okay, that was my statement.
Thank you, Axel. Next, I would ask Francesco to give a perspective from your field of information retrieval. And after that, we will have an open discussion where everyone can ask questions and can make statements. Please.
Thank you. See, more than a statement, I have here a list of questions for you. And the idea is that we should try to go a bit, let's say, critical on these topics. Before I was a bit critical on symbolic reasoning, and now I want to be a bit critical on sub-symbolic. But first of all, I would like to discuss what is the difference between symbolic and sub-symbolic, because we have been talking about that, but we have not made, use any definition. And I would like to cite a definition by David Chalmers that maybe you heard. He's professor in philosophy and neural science at New York University and is co-director of New York University Center for Mind, Brain and Consciousness. So the difference between symbolic and sub-symbolic, according to his definition, is in a symbolic system, the computational level coincides with the representation level. In sub-symbolic system, the computational level lies beneath the representation level. So it's just a matter of the semantic, where the semantic is. He has also a second definition. It is a symbolic system. The object of the computation are also objects of the semantic interpretation. In a sub-symbolic system, the object of the computation are more fine-grained than object of the semantic interpretation. So this is just to make the example. So large language models are exactly like that. So you have the computation level is at the level of arrays, now vectors that have an implicit semantic because they are representing concept, but the semantic is not at the level of the computation. We perform just the multiplication, sum, addition, while in the symbolic system is the opposite. So, but at the end of the day, all these methods are compiled at the lowest level, at even a lower level. So why we have to care? So the question for you, I'd say the first question for you, and also, so why we have to care about that? Just because there is this mismatch of the representation and the semantic? So that's the first topic. The second topic is something that you mentioned in your presentation. It's about the errors of sub-symbolic approaches. So we have seen here the case of the ants with 4 legs. Now, these models, deep neural networks models, are prone to make errors, which are not the errors that we will make. No? And why is the reason for that? The reason is that the architecture for problem solving is completely different from the architecture of problem solving that we are using. So in more technical, ways, the bias, the structural bias of the model is completely different from the structural bias that we have. So these two approaches, we will never probably reach the accuracy of 100%, but the problem is that they will make a completely different errors. So we will never be able, even if we push this with more data and more fine technology, we will never be able to push them to be as intelligent or even as stupid as we are. So there will be always a difference between the two approaches that is not solvable. The third topic that I want to discuss with you is the emergence of intelligence from sub-symbolic models, because this is, I think, the most surprising effect. Now, so when we built this large language model, we were thinking just to generate language, but at the end of the day, they are able even to perform some kind of reasoning, some kind of mathematical computation. So this is showing, by the way, that again the fact that the semantic is at the level which is different from the computation. So the computation cannot make us to predict that there will be a certain type of semantic. That's also very, very interesting, but also this has an implication with respect to the research methods. So what we should do? So if models like that can have a behavior which is non-expected, how we can predict their behavior and how we can direct the research to models of a certain type with respect to models of another type. We can only, let's say, implement and try and see and watch what they are able to do. So what is your, again, position about that? Because I think this is a very important issue. Related to that, I think the last topic that I wanted to put on the table, because otherwise we would have to have much time for the discussion, is the level of plasticity of these models. Now, so one of the major problems of these models, right, still now, is they cannot evolve. So you train them on a lot of data. Actually, you have to balance the data with the capacity of the system in order to get the best results, but they will never evolve. So if you give more data, they will typically not improve their performance. You have to retrain them. No? So you have to start from scratch, essentially, and then retrain from them. So there is something that is now, let's say, the research is trying to do, which is basically very simple. So forget some of the parameters, randomize initially the parameters and retrain them, but are very, very, very simple solution from my point of view. So this problem of plasticity, I think, is the key problem. Are we able to design in the future, this is, let's say, or we will be able to design in the future models that are a level of plasticity which is capable to build the structure of the network and restructure the network according to the data that have been shown, or will be always limited to have a network of a fixed structure that will not be able to evolve, and for that reason will not be able to go above the limits that you have shown so far. So that's let's say the 4 points that I put on the table. I would like to hear your opinion about that.
Now I would ask you, Sepp, to briefly respond to the statements of the panelists. Maybe we start with Francesco. Yeah.
I forgot everything. Can you perhaps remind me the first point, then we can go through it.
Okay.
But, I'm not a large language model.
No, sure. The first point is about the real difference between symbolic and sub-symbolic. This semantic level, which is different from, let's say, the operational level. This is the first.
Let's now. I can only remember one question.
Okay.
Because I have limited capacity. Yes. You're right, especially in the sub-symbolic AI, I did not see what I would say abstractions. What we did is also the large language models work on words, tokens, stuff like this, but they're human-made. These are human-made things, and they are symbols for me. If you work in language and these symbolic things, which have a semantics, because if you say tree, it's something or a group of things which is out there. But the large language models only see statistics among the symbols, is making symbol statistics. And therefore, I see some intermixing of things like this. Also, what I'm waiting for is that AI systems, and I talk about sub-symbolic AI systems, produce symbols, produce abstractions, have something seen in the world, groups them saying, I have one word for it. And probably one of the largest discoveries of humans is language. Because with language, you make abstractions. You can say something about the future. You can tell others about things. Run away from a lion. You saw Thomas shot was a lion or a tiger. I don't remember. And it don't have to be exactly pixel by pixel the thing. Even abstractions, this kind of animal can be dangerous. And this is very helpful. Abstractions helps us to understand the world. We do abstractions by physical laws. The moon goes around the Earth, as far as I was told. I didn't check it. And you have only the location, the impulse, and perhaps the mass of the moon. It's a very abstract representation of this real-world object. And I'm waiting that sub-symbolic systems come up with abstractions which I then would say is symbolic stuff, which you can interrelate.
The second was about the errors. So the essential problem of these methods will always do errors that we will not do. So they will never be able to fix. These problems are not fixable. So you will never get 100% accuracy clearly, and the errors will be unexpected. So it's a structural problem. Do you agree with me or not?
I agree, and even humans make errors, as far as was told, and systems make errors. You said it already, they're different errors, but different systems are prone to different errors. And they will be there. For example, if you train these new databases, now large language models, by predicting the next word, if there's no fact in the input, if you cannot store facts, you have to come up with something because you have to predict, you have to produce the next word. And therefore, they will make errors, which is hallucination. And by the way you train them, it cannot go away. It's inherent. And if I would be super surprised if these errors would vanish. They cannot vanish because it's in the system.
They vanish only if you do reinforcement learning. So if you tell that this is an error, they don't do that anymore. That's the way normally now I solve this problem.
Yeah, you can target some errors, but then there are other errors. You cannot target every kind of thing. If you make this kind of error more often, then you can learn not to make it, as we humans do. But it's a structural problem, as you said correctly.
So the last topic, two topics.
No, we have 4 or 3.
Yeah, but I collected just to leave space to other questions. The last topic was about the fact that the structure of the model is fixed. So they are not capable to learn the structure of the model. So in order to understand what a model will be able to do, we typically, let's say, implement with some heuristic some new structure like your structure, and then you discover that this model is capable to do certain type of things, but this clearly is not scaling up. So we need to go to a meta level to learn the structure of the model. What do you think about that?
This is known under the term inductive bias. What kind of models you do. You can even put in the structures physical laws, stuff like this, and constrain your models. And in machine learning, there were 2 big groups. And this was nice with vision transformers. Some said you have to use like CNNs with convolutional neural networks, which are more vision-like, pixel nearby, have the same color or intensity or whatever, built in the bias you know from nature, or make a big model completely free. And if you have enough data, I think you can, this big unbiased model, which can do everything, it can go down to the right solution because you have enough data. And others say in the machine learning community, you have to implement structures. And this is knowledge we humans have, and use this structure to constrain the possibilities. Even in situations, if you don't know what to do, you use physical laws or whatever. At least you don't violate those. In the moment, it's more than that's inductive bias field is winning with graph neural networks, physics-informed neural network, stuff like this. There's more going on. Instead of making a huge system which should do everything, not designed for one specific task. But yes, probably we have to build in structure. The direction is going there, which is inductive bias. Build our structure such that's good for something like LSTMs is built to store stuff. And this helps.
Thank you. Axel, do you also want directly to ask some questions to Sepp?
Maybe to both my fellow panelists. So basically, as I said, or wanted to make clear, I think we have built tools that are more efficient than models, that models can use, and that's what's happening. And so many of the questions where models go wrong were going in the direction of asking about things that where we have tools that we know work very robustly. So what's your take on that, on both sides?
I have an advantage. I don't need the microphone. I can overspeak. We saw it in AlphaGo or AlphaZero. Monte Carlo tree search is a classical symbolic method. It's always a smart thing to use this symbolic method, which are tested over decades. You know their advantages, disadvantages. To ignore them would be stupid. A question is how to use them effectively, how to use them in the right way. That's not always clear, but of course it's important. Like we heard already today morning with RAGs and stuff like this. Perhaps, and you also mentioned, perhaps you use these large language models, which are databases, only as an interface, only to summarize stuff, only to make a vector out of text or what stuff like this. Yes, we need those methods.
Thank you for this initial statements and the initial discussion. Now I want to open up the discussion to everybody. So please, if you want to ask questions, then raise your hands. Somebody will come with a microphone. And before you state your question, it would be very nice if you would briefly introduce yourself, just saying your name. Thank you.
Hello, my name is Robert Todd. I'm a teacher at the Faculty of Medicine at Comenius University in Bratislava, but I'm also a computer scientist, not anymore in field. And my question would be back to your response that basically all we need is more data and more data and more data. And I'm wondering whether this could solve the fundamental problem that the answers we get from ChatGPT or other kinds of or outputs from generative AI are probabilistic. And can I, for example, at some point get an answer from ChatGPT or some other model that I simply do not know because I searched all my data and the highest probability is that I don't know. I do not have answer because I tried many times asking some questions which I knew that the AI systems wouldn't know. For example, where in some Slovak translation of the book is this person mentioned the first time, and they always generate you some fake data because it's probabilistic. So can we solve this problem that it will always generate something by simply feeding in it more and more data? Thank you very much.
I guess I will answer this, or okay. Welcome to Vienna, Robert. First of all, with scaling up more data, no. Here we reach the limit. We are saturating. Both from the data, we don't get more data. and also the model size. At some point, you cannot pay it anymore, or you cannot handle it anymore. There's a limited saturating, and it's known that we used up all our, at least, text data. Also, producing data using synthetic data does not help. It even hurts, because distribution gets smaller and smaller. You lose variety, because you produce some more common stuff, and the other method learns some more common stuff, and you lose the variety of topics, text, and stuff like this. Synthetic data does also not help. You also asked about, can we do something about this fantasizing hallucination? No. If we train the methods like we train them, they are forced to produce a word from the beginning. So this is a neural network not trained, starting from somewhere, and you force it to produce a word. It does not know anything. It had not seen anything. And that's the basic. You force the system to produce a word, and then you say, no, you were right or wrong. And later in inference, you also force it to produce a word. And you don't ask it, do you have knowledge or not? We have a research group now where you can perhaps flag or indicate whether it starts to hallucinate, because about uncertainty. If it has seen it in the training data, the fact again and again, it's more sure on a semantic level what to produce, not on the word level, but on a semantic level. If it's unsure, if we can say produce this or this or this is possible, you know it's not factual, it's not fact-based. We can flag it, but we cannot solve this problem because it's inherent how we train our methods. More data does not help, and we cannot solve it, but we can live with it.
Axel, you want to add?
I just want to add that this is something that probably a first-level computer science student would be able to program in a database and write the query that retrieves the right result if you feed in the book in a scalable enough database. So that was exactly the point I was making. Yeah? So there are some methods that we know that can be used for many of these challenging questions. We have solutions, right? So it's the difficulty that I see is that I don't see yet clearly how we can train models to always use the right solution and the right tool. So there is quite some research going on in this respect, but it's not yet all fully automated. So this is something that I believe at least not yet being done by sub-symbolic methods, and where one should look into.
Do you have further questions? Please just raise your hand. Yes, in the back, a question.
Frank van Harmelen from Amsterdam. Thank you for your talk. The issue was raised about shouldn't we learn the architectures, right? So would you agree with the following, that in the current state of machine learning, there is essentially no theory about architectures? So we have a whole bunch of architectures, and we try them, and we know by empirical trial and error that some architectures work for some kind of problems, and so we are stuck in a kind of random walk in design space where we know from other fields in science it actually helps to have a theory where we can predict what kind of machines or what kind of mechanisms work for which kind of problems. Is this, would you agree, or is this a caricature, or would you encourage this more theory formation about the sub-symbolic architectures rather than just doing gradient descent by PhD student, right?
Yes. Because you asked about the result in the Champions League. Yes, Liverpool won 2-1 against Real. Now to your question. That's a problem, because it's at the moment in this field, this is deep learning. It's more engineering, how you build a car. You don't understand it, but it works. And also what we did, we built some B models. Some stuff works, some does not work. But you not always understand it. we are looking. I also showed you this bilateral AI. Do you already have a job? Otherwise, apply. We need guys working in this field. We have to understand it more. We cannot even write textbooks because we have no textbook knowledge. That's a horror. But it's also super challenging and difficult to come up with a theory to understand what's happening. And everything is interfering. You have, as we train these big models, some parameters work and it's going down and everything is decreasing. If you change something, it's exploding, it's jumping out, and it's about weight decay, learning rate, everything, and even the right GPU, if you change the hardware, everything blew up. And you don't know. If you change the precision from FP16 to BF16, everything doesn't work anymore because gradient accumulation doesn't work. Why does it not work? You don't understand. But it's super hard if somebody can bring light in this very dark corner of deep learning. I would be super happy, but I think it's also very challenging. Even Terence Tao did not help us until now.
Thank you.
What's that?
What was the last?
Terence Tao, it's a professor at TU Vienna in mathematics.
Ah, okay. So it's the name of a person.
Terence Tao.
Terence Tao.
Terence Tao.
Tao. No, it was. But to be correct, Liverpool won 1-2-0, 2-0. So it was you were hallucinating.
Sorry, I take it back. It was 2-0. You're right. It's right.
Yeah, you know, based on the statistical patterns, I'm sure 2-1 was more likely.
Yeah. I relied on our XLSTM and
yeah. Yes. So I just was wondering if you or the other panelists have any thoughts on the new paradigm for computer science question with respect to these systems, and also, in that case, what was the old paradigm?
Could you briefly say your name, please?
Oh, sorry. Yeah, Thomas Haig. I was speaking this morning.
Should I start? You're looking at me. Things change. Like in computer science, you have education where you train the people to program. Programming will be, software engineering will be completely different. You have this code co-pilots. Things change. To make comments in your program. I heard from rumors in the early days of programming, you did it by hand, you wrote your comments. Now you have systems helping you things. Things how you work, like in software engineering, change. And I think it's not that you have algorithms and data structures, you think about how to solve a problem, because there are so many people out there who have already thought about this, who already have a solution for this. That you get more the solution, have to verify the solution. To do your own program is stupid because these programs exist already. And there's a paradigm shift. As you come up with algorithm solutions, stuff like this, no. You get something, but you have to check, is this what you want to have? That's for me a paradigm shift, that you go more data-driven. You do inductive instead of deductive. Until now, computer science was deductive. You think about to build a database or stuff like this. Now you learn it. You learn your program, but you have to verify it. That's my take on it. Paradigm shift from deductive more to inductive computer science.
Other opinions?
Your question is the basic question. I think it's the question for this workshop. From my point of view, we are really missing the point. because the two sectors are totally separated, apart from some few attempts to combine the two approaches. The teaching is moving towards the engineering, even in computer science, which I think is wrong. Even if I'm not supporting, some sense, the classical approach, I don't think that we have to move and do engineering, like adjusting weights and finding strange ways to make the system work. So we have to understand. And also is not becoming interdisciplinary, which is another issue, because now has to be interdisciplinary in order to solve this type of problems, including new forms of computation, which are necessary in order to scale up. I don't think that with this type of computer, let's say, structure, we will be able to solve this type of problem, because they are essential problems that cannot be solved if we continue to move in this and in this area. We need some really new things.
So maybe a quick addition. I mean, as I'm working on the University of Business and Economics, we see a lot of people. So I've attended a couple of events where I was a bit shocked being trained here as a computer scientist. People jumping blindly into firing on all kinds of problems. Let's solve this with LLMs. So if this is the paradigm shift, then I think this is a straight route into the next AI winter. Right. I think plus, of course, when people say we will not need to understand and learn programming anymore, that might also be quite dangerous, because then, in a sense, we cut off our ground. Yeah? So I think this is something we have to be quite aware of and try to think about what it can be a very positive paradigm shift in terms of combining methods to be both more efficient and more effective. And I think this is only possible in combinations of methods and understanding methods. And when we talk about teaching, getting back to the example of the pocket calculator that I also mentioned, right? So when this whole hype came up, and also in teaching, you know, we all in our universities talk about what we should teach our students. We should teach our students how to use a pocket calculator. And also likewise, we should teach them how to use these new technologies, right? So when we teach to school children, before we teach them how to use a pocket calculator, we teach them the math underneath. We teach them how it works, and then we let them do it. For using LLMs as a writing tool, we have to also teach first the limitations, what it can and can't do, before we let them just write papers or seminar works with it, etc. So I think it's very important to also consider in the education, not blindly jumping into just using tools as well. It's maybe contradicting what I said before, sorry.
I want to add to this my personal view very briefly, since I'm also a computer science professor at University of Vienna, leading the data mining machine learning group there. So personally, I think we are living in very challenging and exciting times as computer scientists, because now these technologies are really emerging and are touching every field in our society. And as the output in form of language is much more accessible for anybody than it was before, when it was just vector spaces or anything like that, which was limited for expert users. But still, I think there are a lot of open challenges to be solved. For instance, what do you do if you have secure critical applications, if you have applications where you don't have lots of training data, for instance, medical applications with rare diseases, there you still struggle, and often you don't apply any other methods than the ones which were designed 20 years ago. So when you have a real application, a scientific application, it's still very hard to get most profit out of these novel methods. And also when it comes to bias in these models, as you said, these LLMs are like databases, and that allow us to query actually all the texts in our society. It is also stunning to see how much gender bias is in our world. We can study that very easily when we query just an LLM about that. And there's a lot of research which should be made in Europe, according to my perspective, to design AI methods with European values. And this is just my personal statement. I want to give it that point as well. And then I want to ask you, since I have the right to go over time a bit, as we started late, I want still to collect some more questions from your side. Yes, please.
My question is related, Enrico Nordelli again, sorry. My question is related to something you just said about education. The fact that in some sense this tool will change the way we educate people from deductive to inductive, verifying instead of producing. And my question is, are we really sure that professionals in any field, not just software development, in any fields, professional can really verify something that they are not able to produce? Because there might be some subtle issues that fool you in thinking it is good, and unless you have broken your head on this kind of issues, you can't, I mean, it appears that it's good, but then in the end it's not good. That's my question.
I think a very good question. And I think you have to understand your thing, like programming, that you can verify and how to verify it and to understand this is a solution. You win in writing the solution, but you don't win in understanding it. As you said already, that some guys are using large language models for doing any kind of stuff. Yes, it's prone to errors. But to really be thorough to understand it, you have to have a good education to understand it. But in producing it, you can have a speed up. Because many things are very routine, defining variables or whatever. I need 10 float variables or whatever, stuff like this, or a plug-in, a sort, a quick sort or whatever. I don't write it, or I think there you have a speed up. But you have to know the domain. You have to have knowledge. Otherwise, it's not reliable.
Thank you. I think there was one question here. Is it possible to still, do you want to ask?
Yeah, I also wanted to touch on your point of the bias that we're creating with the technology. So I think when we talk about paradigm shift, and someone, I think it was you, talked about this innovator's dilemma, and I see there are some obvious things coming out here, like the point that we are not inside a paradigm when we are using intuition to design. That means that you're outside of the box. But the question I would say is, like, what is it that makes us be outside the box? Because there is a lot of bias in this current paradigm that we're in. So we're reinforcing a lot of stuff that we're already seeing, which is the point on gender or other things that, you know, destroying the environment and so on. Not to go too extreme here, but shouldn't there be some sort of reflection before we go to the next step? Oh, sorry, Erik, I talked earlier. I'm a startup entrepreneur, so I'm very intuitive in this, so I definitely don't do the research.
Should I ask? For me, it's easy because I have this kind of thing here. I don't know whether I understood you correctly. You think more paradigm shift in terms of computing. How we do computing more energy efficient or stuff like this?
Maybe I could...
I could just clarify. It's like the first part of this question is ethical, right? We are now reinforcing a lot of things that we are really doing wrong in society. And the LLM systems are really doing an expert job in revealing this, as was pointed out. So does that mean that we have to retrain the model?
You want to?
You can, if you...
No, first of all, we have to be clear. If we train our model on data, it will reflect what's on the data. And if humans have done it wrong, they will do it wrong. Imagine you train a model in predicting the income of some personnel. and then you switch the sex from male to female. You can think what's happening. But it's not the problem of the system, because it learned it correctly. The error was already in humans. Humans used the data in a wrong way. And it's hard to correct a thing if you have to learn it and say, yes, learn it, but it's wrong. Do it then right. And it's much harder to correct it afterwards, because all the variables are interconnected. If you remove one variable, perhaps the other variables can predict this variable, and the bias is still in there. To get rid of the bias is super hard. But don't say that these systems should do not the errors we are doing, but they should learn from us. That's a contradiction.
So I would say there's a branch of research focusing on fair machine learning, and actually these people are considering exactly this methods, designing fairer methods. And it's from my perspective, this research is just in its childhood, and it's a long way to go to make the results transferable to deep neural networks, because as far as I know, most results are currently done for rather simple classifiers and architectures. And also, as you pointed out, Sepp, often it is that one has to predefine a critical attribute, which can be the gender, and then the model basically tries to ignore the gender in the learning. However, there might be other variables which are statistically dependent in some complex ways from that attribute. Therefore, it does not help a lot to just remove this attribute from the training. But still, what I see it also as a chance, because in the large language models, we have a distilled knowledge base where we can query, and let's say we can put ourselves in front of the mirror to see what kind of biases we have. And we should really invest into this kind of research on fair machine learning. And that is an area, I would say, where also, for instance, the European Commission should invest, because the AI companies probably are not so interested in removing this bias. And this is one thing I want to point out, that also some founders of AI, like Joshua Bengio and Geoff Hinton, they have quite a negative view on the future. So they have visions about catastrophic scenarios where AI takes over our society with very negative impact. And I just wanted to ask you about your view on this kind of statements. So actually I have the feeling you have a more positive view on our future.
I also have this feeling.
May you comment first, or?
Yeah, we'll comment on your statement. So it will be very, very short. From my point of view, this approach, which is debiasing a bias system, is stupid. So imagine you have trained the model to speak as the normal person that is, let's say, here. So that he's making errors, which is making exactly the same errors that are in all the documents that have been used. And then you wanted to fix the problems by telling, no, you don't have to make this mistake. I think it's more intelligent to use another training method. So that's the point. So you cannot expect that this model that has a particular, I call it structural bias, not bias in terms of bad information, but because it has a certain, let's say, set of constraints by construction, is capable to do certain type of things and then fix the errors that by structure this one is not able to fix. So from my point of view, this is not the way to go. And this is also not my opinion, but also if you ask, let's say, to the big boss, even in say Meta, they say this is not the solution for, let's say, a bot that will tell you the truth. This is just a way to build a bot that will speak as other people are speaking.
Sorry, yeah, maybe one short comment, but then I would like to give the word to Sepp to answer.
Yeah, maybe to play the ball to Sepp, I think this is exactly what we're up to in the BLI project, where the goal is to build a robust and broad AI that using methods from different sides of AI, not only building end-to-end sub-symbolic methods, but also methods from, for instance, causality, also how to include formal and established policies and norms into the inferencing of AI. I guess this is exactly why all these people you saw in the picture came together to address these questions together, right?
I think also start with this one. I agree to you, Claudia, but I formulate it now in a different way. She said, she didn't say it, but I put it in her mouth. We don't have to fix the models, we have to fix the humans. Because with the models we see the errors we humans do, and if we fix the errors the humans are doing, we get better data and better models. And perhaps it's more rewarding that the humans do not do the errors anymore, who decide about the salary or what penalty you get if you a criminal or whatever. Should I go ahead with Joshua and Geoff? Oh yeah. Where should I start? Yeah, it's a little bit negative. They moved their view, but there were three humans. There's something behind it. Geoff always tried to understand how the human brain works. If we understand how the human brain works, we can build an artificial intelligence. We can build something. And then these language models came out, and all the resources within Google were put to this, and it was kind of frustrating. And he saw the power, and they can do much more, and he was a little bit overwhelmed. And okay, Joshua is because I talked to them also. But what I'm missing is the scenario, the mechanistic thing. How should AI overtake something? We define the objective. If a neural network have to distinguish between a cat and a dog, why should this AI say, hey, and now I will be mayor of Vienna or whatever? It's trained for this. These systems don't live in evolution. In evolution, the things survive, which compete about resources. We do the evolution for the thing. If there's some error in a model, we switch it off. And we're also not scared about a pen. Oh, the pens will take over the world. Here we see they cannot do it, they're not designed for it, they don't have the thing. But we, it's an evolutionary thing, we decide what's surviving, what's not surviving in terms of AI. And that's a big difference than evolution. They're not in evolution, that's a big mistake. And another big mistake is intelligence does not necessarily look for power. We saw it also in the Nazi regime. The intelligent guys, scientists, moved out of Germany. It was not the ones who were in power. Sometimes, if I look around the world, don't interpret me wrong, I'm not convinced that the most intelligent people win the elections and everything in different countries. And I think intelligence is not necessarily looking for power. Why should artificial intelligence looking for power? If it is intelligent, it can get the objective in other ways, not by hunting humans like the Terminator, stuff like this. This is also a misconception. There are so many misconceptions coming from Hollywood, and therefore there's some guys are frightened that things like this happen. I'm not. I think we should use this new technology as our tools to improve. It was one of my first slides. Climate change, health, produce fuels, mobility. We should use it for us to have a better life. for us to make this world a better world. And I think I don't see any dangers that they will take the power.
Thank you very much. So also in the interest of time, I will close the session now. Thanks a lot for all your questions. I think we could discuss for several hours, but I hope you will have the chance to meet also the others and each other and continue discussing during the workshop. So thank you very much.
Sure.